Good morning, everyone. Let me just minimize. Just want to see my face. All right. Good morning, everyone. So thank you for joining this tech talk. So today we're going to be talking about processing electron microscopy datasets with Python. So my name is Roberto dos Reis. I'm a research assistant professor here at MSc, and also I act as a scientific officer for Professor Dravi Group. And also I work for Nuance Center as a part of the EPIC team. So I was discussing with the organizer of Tech Talk before. There might be a part two of this because I tried to condense a lot of content in 1 hour. And I know you might have like a lot of questions about it. So I'm just trying to go slow and then that you can follow along. So the idea here is just to cover and give you like some tools, right, to process some of the data that you acquire with SEMs or TMs, right? This is the focus of this tech talk. It can be something like very basic, as a cropping the data, loading the data set, plotting and preparing a figure for a paper, for example, to very complex data sets that, for example, like an in situ TM analysis, or like 4D STEM, or like a spectroscopy, or something on SEM, for example, like a TKD map or EBSD map. So I will do the first part today, and then let's see how far we can go, and then of course, I can ask questions along the way too. So I will start with a brief introduction. What is data, right, in electron microscopy? So you probably see like a lot of like beautiful images. So I picked two here as an example, like SEM images. They are like usually beautiful, and the high resolution STEM image. So you see, for example, in terms of length scale, you can cover like a pretty large range of it. Although when you capture your images, they're usually like this, right? They are like a grayscale, or sometimes they have like an unbalanced contrast, or regions that you want to highlight are not highlighted in the image that you actually acquire, like the raw data, right? And there's much more information in those images. You just need to have like the right mathematical tools to do that, right? So for example, we can extract like the structure, or like the morphology of your sample, like chemical composition if you do spectroscopy, or for example, analyzing like a HADAF image in STEM, crystalline structure, orientation, do particle size statistics if you working like nanoparticles, for example, size of the grains for like polycrystal samples, atomic arrangement order, to like high resolution TM, STEM, and much more, right? So you usually come to your to use SEM and TM with some idea in mind, and you try your best to extract that and get like the right data set. But sometimes those informations are hidden in the image, and then you do have to have like some tools to do that. In most cases, you use like proprietary softwares, like for example, like digital micrograph from GitHub, or some software from like Oxford or Bruker. But they sometimes are like limited, right? And you want to have like more information from a sample, and so therefore you need like more tools to do that, right? So the idea here is just like to cover different dimensions or data dimensions, right? From the simple like 2D data sets that could be an image, right? An SEM image. It could be on the STEM or TM, could be like a high resolution STEM image, could be electron diffraction, you name it, right? To like 3D data sets that could be, for example, like an in situ STEM or in situ SEM that you add time as another dimension. Could be spectrum images, for example, like EOZDS maps, or like in SEM could be like a TKD map or EBSD map, where you add information, chemical information about the sample, and then you map that over a specific area. Could be a 4-dimensional data set, for example, tomography plus a spectrum image, say, for example, like EOS tomography or EDS tomography that can be done in like a STEM, for example, in a TM machine, or it could be like a fib sectioning with some chemical information on EDS. It could be also like a 4D STEM, which is like a capture information from like a two dimensions from image plus 2 dimensions from diffraction patterns. It could be more than 4D. Then think about could be an in situ 4D STEM, which have I even don't have an example here because it's a little bit more harder to process. So you have in situ 4D STEM, which is like 2D image, 2D diffraction plus time. It could have in situ spectrum image that have 2D image, 2D use EDS plus time. You have in situ or a combination of tomography in situ SI, right? And then you just get more and more complex. So the idea today is start with the simple one, and let's see how far we go. I have prepared like some codes for all of these possibilities. So you're gonna have access to that after this talk too. So the idea that I'm gonna code live with you. So if you want to follow along or just like watch the recording of this, you can access this GitHub repository. The URL is here at the bottom. So I'm gonna just jump to that. So if you can see my web browser now, this is the repository that I created specifically for this tech talk. So you're gonna access by typing the address or in that link on the QR code. You're gonna have access to the data sets and the codes here. So there are a couple of like some requirements that I have to run after that. Just if you are familiar with like Python installation, you can use like Anaconda, for example, download that. I have the instructions here to do so. I do recommend to create an environment for that. And I show you quickly how I operate on that. And then at the end of this, this is open, right? So you can always like contribute if you want. If you are a little bit more savvy on GitHub, you can just do directly, and then I'll be controlling like the pull requests, etc. So let's jump right in. I will control the time. I'll try not to spend too much time. So this is one way to do it, right? You can do using everything here will be like in Jupyter notebooks. So you can open a Jupyter notebook in whatever platform that you use. I am particularly using here VS Code. That's I have my codes here on the side, and then I have everything in my folder. So I do created an environment previously, so you can follow the instructions to do that. So I have here my environment called Advem. So that one, I have installed everything that I needed for this talk. But of course, you can ask questions and send me emails after this too. So the first idea is to deal with, actually, this one, 2D image analysis. So the idea here is just like to know how to load, simply load images, like do like simple cropping, apply some filtering, and prepare images for publication. So I do have a couple of images here that will be available, like a high resolution STEM and then an SEM image here that I'm going to be operating on. So first thing here, I'm going to load the packages that I need to use. So pretty standard packages in Python here, the matplotlib and NumPy and SK image, just to read the data. Here I do my loading, right, which I added already here a couple of options for you. So you can just uncomment if you want to load a different image once you download everything from GitHub. I do read the data with IO from SK image, and I display the image. Very simple, right? So you don't need, open anything else. I'm just gonna run that. And this is my simple SEM image, beautiful image that was provided by Nick to me. So we can do with just like one quick set of commands here, we can just plot an image that looks nice, right? So of course you can do a couple of other things to prepare this to the level that you can submit for publication, right? For example, you might want a crop region here of interest. You might change the title. You might change the color of the title. You might not want to have those axes here shown. For example, a quick thing that you can do, just turn off the axis and then plot that. That looks better, right? You can do a quick change of the title, for example, change the font size. I don't want it like that looks like too big for me. I just do like 8, and that just like small. Maybe it's too small, just like 10. Right? Uh, and let me just show that. And you can just like change from bold to like italic, for example. And then have an italic, which seems to be broken. And you can do like center, the localization of the center, left, whatever you want to do, right? So like I said, you might want to crop that image in a certain region. Say, I want to focus on this part here. That there's something interesting here. There's like some grains on top of some substrate here. Then I want to focus here because you have like kind of like an interface between those two materials, right? And I want to emphasize one, let's say. So I want to copy that, and then you can simply do the cropping by basically like slicing your image, right? So you can define like the start row, end row, start column, end column, and then just like crop directly from the image. Since the image here is basically like an array, right? So that defined by the pixels. So you can just do that by changing those numbers programmatically, and then just crop that image, right? And then I focus on that part that I mentioned. Again, I added the title here. If you don't want, if you don't want to add that, just comment this off. Okay, for example, have this. This looks a little better, right? So another possibility here that the users actually do a lot, and I've seen a lot in publications, right, is that using like image filtering. Sometimes you acquire like data that are a little bit more sparse, or doesn't have a lot of those applied to it in TM, for example, or you acquire with like less pixels and a little bit like blurred. You want to filter that and get a little bit more the contrast out of that image, right? They can do like a simple filtering, right? So I added here a couple of filters. Those two are probably the most popular, like Gaussian filter and the median filter. You might see a lot of publications with those two applied. And one thing that I really recommend to you is just that anytime that you apply those filters, just mention on the paper that you did so, and then add the weight of that. So say, if you apply a Gaussian filter with sigma equals 2, you just do that on the caption, right? And I will show you here like a couple of examples, like by changing that number, how that means to the image. So again, I go and import the packages here that I need, and then the functions within those packages, right? And I do a quick like function here, define a quick function called like plot FFT, because I want to show you how the filter affects the reciprocal space, or by doing the Fourier transform on the image, and then apply Gaussian filter and the median filter to compare what they do to your image, right? So in this case here, the Gaussian filter that I apply, I have the sigma equals 4. That is a variable within the Gaussian function. You can change that. You can do whatever you want. You can do like sigma, say 2. Let's do sigma equals 1 for now. And the median filter, there's this variable called like footprint. That's basically like the disk size of the medium filter. You can definitely like check how what's the math behind the medium filter. For short, like as you increase the size of the disk, it gets like a little bit more blurred. So it acts almost like the sigma here. Not the same, but it looks like the sigma. And again, I define a little bit of the plotting here. It's a little bit different because now I want to plot like all four in the same figure, right? So that's a little bit something that you learn from the other plot. So you can add like subplots, right? That is ready for you if you want to just like plug in your image here and do the comparison with the FFT. Right? So if I run that, we have the Gaussian filter image on the left, the median filter image, and how it looks like in the Fourier in the FFT, right? So you see that, for example, let's do a quick exercise here. If I do sigma 0, that means I didn't apply any filtering. This is how the FFT looks like. You see, there's no, it doesn't drop quickly, the contrast here. So if I add, for example, I don't know, let's do like 5. It's a little bit more dramatic. It really like drops the intensity here, and you see how blurred is the image on the left. So in some cases though, this might be useful, right? For example, if you want to do a edge detection, for example, on your image, that might be a step that you wanted to do beforehand, right? Blur that because that changed like the histogram of the intensity distribution within your image. So it's easier to pick up some of the edges, for example. On the other end, you lose some information, as you can see on the FFT, right? So you don't have that, say, quote unquote, scattering function here all the way to the end, right? So kind of like crop some of that. So you lose resolution. The same way, like if you're familiar with like electron diffraction, take a diffraction pattern and you measure like the resolution of your microscope using the diffraction pattern. It's like similar here. Same thing for the median. So like if you do like a larger one, let's just like do a little bit more dramatic here. You see how that kind of gets like washed almost. One advantage of the median filter, something that I mentioned earlier, is that that's why this is one of the preferred methods. You don't lose a lot of resolution as you lose using Gaussian filter. Something to keep in mind. But you get like the image a little bit more like washed for some reason. So perhaps like after you do like filtering, a quick filtering, quick cropping, you want to prepare that for publication, right? And then be ready to add to your paper. So usually want to like enhance quality, make sure they like highlight whatever you want to highlight, and you want to make them visually appealing too, right? So like adding colors, etc. Adjust brightness, do like this what we call like histogram equalization or like contrast stretching, like where you expand the range of intensity values to like highlight some features. So you can do that. So again, here as an example, I will import this exposure function here. So again, this is the same function. I'm just repeating here, just because it's easy for you just to run those cells like separately if you want to. So we have the first one is contrast stretch, and the second one is equalize image. I will show the effect that on the histogram later. And here I added just like a plotting function, right? With the color map gray for now. Later I'm going to show how you can play with that as well. Again, so let's run that. Make sure it's working. Again, I'm just plotting on the side the FFT just for comparison. But here you can see like the contrast stretch image and the histogram equalize. You see, in this case here, I feel like both more or less like highlighting the same thing. The histogram equalize kind of like uh makes this area here a little bit too bright. But depends what you want to highlight, of course. So if you want to highlight just this, perhaps the contrast stretch is a better option in this case. So if you want to look at how that affects your actual distribution on histogram. So here's a little bit of explanation of each one, but I'm just gonna jump right in on the code and just show the histogram here. So this is the original image, right? That it spans from like 0 to 55. This is 55 channels on a grayscale. So if you do a histogram stretch, that basically like the histogram stretch just basically like expands that intensity pixel values and then increases the dynamic range of images, meaning like it gets like this distribution here and make more or less equal across the range, right? This is I plot up to 25 here because it also does is like reduces a little bit the range. So that's something that this contrast stretch also does. If you do like equalize image, this is a little bit more familiar, I guess, to you. And I've seen people doing that a lot also in publications. That we have a little explanation here. It's basically like just do like this redistribution of the intensity values, right? Again. And one key thing here that all the channels are like equally represented. So we kind of like balance out the image, right? And that's something that you might want to do. For example, if you go back here, if you have like a very a background that varies a lot, for example, right? So think about this image if you have like a very dark area area here compared to like a very bright area on the lower left. So that might be useful for that. And that happens a lot, especially like if you have like shadows on the image, like on SEM, for example, on a TM, you have like some sort of like a not very parallel beam on the TM measurement, or like your stem image, it is a little bit like lower mag. That happens a lot too, because of like the way the beam scans across the sample. So that's why probably this one might be the most popular in this case. And of course, you can always like change the range after, right? Say if you want to make a little bit more balance here, you can change the range that you plot. Just give more channels to the plot at the end. So now after doing that, so you might want to add a couple things, for example, like scale bar, very important. And in some cases, which actually I like to do, is just like plot the intensity, especially when you're comparing data, right? So say you collect the data today and you collect the data from the same sample tomorrow, you might not have the same parameters as the same, you might have the same parameters in microscope, but the microscope might be behaving like a little bit differently in a way that you have some unbalanced contrast. Very minor, might be important if you want to quantify, you want to do quantification, right, in a sample. So a couple of things here that I added on the cell too. If you want to add, for example, like a small caption, like figure A, figure B, scale bar, like I said, and intensity. So if I run that, quickly you have that. Here you can change. So this is 5 micrometers here. You can change if you go here on the scale bar. So we can adjust that depending on the image scale, right? So you can change here. This is in pixels. So depends on your calibration, you can change that. You can also, if you want to add a variable here and just like change on top, say calibration, something like that, and then add a number, and then just add here calibration. That would also work. Then it's a little bit more flexible. for you. You can change like the color, right? So we have in black now. So let's say if you want to do red, probably work. And the intensity here is in grayscale because he's still operating on in a grayscale image, right? So continue on. So at the bottom, if you want to add, for example, a caption, right? So here added as a markdown on the Jupyter Notebook. This, when you export as a PDF, for example, that looks like a caption, right? So you can do your whole like image processing, for example, that goes in your supplemental information in your paper like this, right? And then the readers can like reproduce the way that you plot your data, for example, which is like very useful. And then helps to validate your results as well. The community helps the community to validate your results. So other things that you might want to do here that I show at the bottom is just like adding like labels, right? I kept this at the top, but you can always remove. And you might want to add this, right? This looks a little bit more publishable, I would say, with the scale bar. And perhaps if I change this one here, that would be probably ready to go, right, for submission. So if I do just change, take out the title here and take out the title from here, it should be fine. Yeah. And then I added like 2 different color masks, by the way. Oh, sorry, this is the one here. Sorry. Yeah, this guy here. So this, for example, it would be like good, right? So it has the labels, it has the scale bar, you apply some filters, some intensity equalization or the contrast stretch. Perhaps here you might want to plot with a little bit of a different range just to avoid this bright area here, but more or less like good for submission, right? So another thing that I can add, which you probably saw already, we can add colors, right? Say there are like a lot of options for that. I plot 2 of my favorites here, which like red to blue and the traditional like varieties that comes with kind of like a basic Python or matplotlib option here. But you can just go crazy. That's too many options. Say here, I added in this case here, right, during the plotting, right? So I apply a color map to that, and then you have like 2 other these 2 other variables that represents the images like colored. So you can do another one that is like here, like hot is a good one. Really depends. If you wanna highlight like a large variations in the sample in the image, you might want to have like a divergent color map, like red to blue. If you wanna perhaps you have like some sort of like electric field on that, so you want to plot as a vector, for example, you might want like a cyclic a color map that goes with the color wheel, for example. If you want to do like directionality on a sample, depending on the contrast, you might want to use that as well. More like a cyclic color map. Or like, simple color maps like, just red or just blue or just green, right? So if you want to like just like detach channels, for example, from an image, you can just like separate in red, blue, RGB, right? So yeah, there you go. So you have a hot one here. And you might want to change, in this case here, also like how the scale bar is plotted, right? You can how you plot the scale bar. So in this case here, at the end, you just go in and save, right? So you have a save function, and then you can define like the dots per inches. Usually publications require like 300 or more. So you can do that here. You can do like 600 if you want. You can save as in a different format. In this case here, I'm saving as PNG. JPEG I would not recommend in general, but tends to be fine. Better if you save as PDF usually, or TIFF, the full TIFF, not the 8 bits. But with this, like the idea here is just like, okay, after this, in like what, 20 minutes, 25 minutes, you can leave with a way to plot your data, right, for a publication. And this looks good, right, for presentation, etc. Well, so let me go to the next, which those are like simple images, right? Like I mentioned, which still can get a lot of information out of that. So getting a little bit more complex, I'm gonna show an example on using a high resolution stem image. So the idea here is just to understand how to apply noise and filter just to emulate a sparse image, for example. If you acquire data from a sample that might be a little bit like beam sensitive, you might have to use like lower electron dose in this case, so you kind of have like more noise. So how to get rid of that, more or less, right? So you cannot never get rid of completely of the noise. In this case, here is a high resolution stem. So we want to learn how to do how to localize the atomic columns, and then do a quantification, then intensity quantification, using like double Gaussian in this case. And then one thing that I added here to the end, might not be able to cover that today, but it's more like applying like this Bayesian framework to quantify the atomic columns more reliably, I guess. Again, I provided like 2 data sets, in this case 2 images. So I will start again with like the simple thing, right? Like I did previously. So just like, simple packages, how to read the data. This one in particular has a interesting like format. This is from it's like a Thermo Fisher format. So we can use other packages to read that. To and just like extract like the array from that and plot it. And this is the raw data, right? This is how it looks. This is a high resolution image of a gallium arsenide inversion boundary. So there's a region here in the sample where you have, instead of like gallium arsenic, you have arsenic gallium, which I don't know which one it is, because gallium and arsenic are very close in the periodic table. I want to use the intensity to quantify that. The intensity on this Z contrast image to quantify that. So first thing before that, get to the quantification. Perhaps you have a similar sample, but you have to acquire with a much lower dwell time on your stem. So it might be a little bit noisy. So it might have like a very noisy image. So how to denoise that, right? So the simple way to do it is just apply the same filter that we did before. So this is more like another example where to apply like the Gaussian filter, right? And then in this case here, I show like 3 examples with the 3 different noise levels. In this case here, I put 0 just like to show like the raw image, and then I incremented the noise. And then you can play with that as well. I'll just change just to see how the Gaussian filter acts on those images, on those different levels, noise levels, right? And you're welcome to try like different filters too, right? So now you know at least like 2 different filters. So you can just copy from the other notebook and then change here as you wish. And let me show how that looks. I did it for like 3 different examples. So in this case here, no noise, just basically a plain Gaussian filter on the image, which helps, right? As you can see, it helps a little bit already to clear up a little bit the image. This is with a little bit more image, and then this is the filter. This is with a lot of noise, and this is the filter, right? You see that it does recover a little bit, but it's still like loses a lot of information here. And you might have to play around with the different sigma values here to be able to recover. And you might not even be able to recover at all. And you have to use different approaches to do that. Like, for example, operating on a reciprocal space, do like some sort of like a pattern matching, or some other like more fancy techniques like machine learning here, which we're gonna get to that at some point, but not today. So one thing that is interesting to see always when you have like a noise image, just do a comparison on the Fourier space, right? So basically like to understand how much the noise is and what's the strategy that I want to apply to reduce that, right? And what's the intensity of the filter, or even like what kind of filter you want to do it. If it's like perhaps like not even a Gaussian filter, it might be just like a low pass or high pass filter, or a top hat filter, or whatever combination of that. In this case here, let me show you quickly how that looks. So I have the same set of images that I show up here with different like noises, and then on the right, like the filter. So here is basically like zero, just the raw data, and this is the filter. You see how that intensity drops and you lose a little bit of information. Although in this case here, a lot of the information is contained in this area here, right? So you don't lose a lot of information in this case, in this particular case, right? So this is how it looks like, the noisy image with just a little bit of variance here. The filter looks pretty much the same, right? Even if you go to the image, those two images look like very similar. You don't lose a lot of information. You can still see like this dumbbells. You can still see like this dip in intensity here in the middle and here as well. So you don't lose a lot of like contrast here. On the third one here, you don't even see the dots, right? That represents the periodic structure in the image. So even with the filter, it's difficult to recover the information from that. One thing you can do here, quick exercise, is just change the variance here, or the sigma value. Let's see if I add, let's just do this half. Let's see if it gets a little better. You get a little better, but just for you to compare. There's a filter, and here FFD. You still don't see. You started to see a little bit. Maybe it's too small. Let me see if I can make it larger here. There we go. You can start to see like the dots here. So you get some information about the periodicity of the sample. So now after that initial filtering, you might want to localize the atomic columns, right? So we can use this function within the SK image, which is like pick local max. That's like a simple way to do it. And then not only works for this type of image, but it will work for any like image that you want to localize a peak, right? Say you have a distribution of nanoparticles and you just want to localize the particles. This could be a good way to do it as well. So it works like a different resolutions, not only like for high res images. Then you have a couple of variables here to determine. And then this, of course, you depend on your image. But say, for example, like the minimum distance between the peaks, right? So that's one. And then the threshold of your image. Say, just to explain a little bit about this one. So if you go back to the high res image, right? So you do have like some dips on the in intensity here, and then you do have something in the background, right? So you might want to distinguish that background and create a threshold for that. So when you run the peak finder, that will not localize or will not determine like this region here as a peak, right? That one is one strategy. The other one is like the peak distance, right? In this case here is a little bit more tricky because the peak distance between those two atomic columns here, it is smaller than this distance here from in between the columns, right? So we have to be careful with that. So we change a little bit the variables, and if you plot on top of the image, that how it looks like more or less. So you still see that it does capture the peak, right, as we expected. But in some cases here, you might see here, if you can see my the arrow, there's a little bit of a offset, right? Which is okay if you want to just to determine like how many atomic columns exist, right? For example, but it's not good if you want to determine, for example, strain, right? Because the strain depends on the position of the atomic column, and that atomic column might not be displaced like it is shown here. This is because, like I mentioned earlier, this function is a very simple function just to find like maxima within your image, right? So you might want to use a more refined method here to actually capture exactly where the peak is. So I will show you an example later so you can build from that. So using this one, you can also like extract the intensity. That was the first goal here on this was to actually localize the column and then map the intensity, right, to determine if it was gallium or arsenic. In this case here, I just import another function here called util, and just basically to normalize the image in this case. Use this same thing, just pick local max, just repeating from the previous cell. And then I map the intensities for each one of the peaks that I collected using this function here, right? So basically, like the intensity here is determined by the actual like the pixel value at that position that was determined by the peak local max function, right? Say if it's a little bit offset, that will pick that intensity, right? Which could be, for example, something related with your detector that might have like a unbalanced like pixel intensities, things like that can happen. So it's good to do like a normalization before, like I did here. And that will like help you to determine what's the the actual like peak in that case. But again, that would do like the maximum value within that column, right? Which can be a little bit off center in this case, right? So because you're using just a simple methodology here. So nevertheless, this works, right? So depending if you have like maybe like a better image than this, that will be sufficient, right? And then in some cases here, you can see like very well like the difference, and then it looks very nice that, for example, on the left side, you have most of the most intensive columns at the bottom, and then on the right side, you have like the ones that are more intense at the top, like meaning like, and here have the boundary, right? So that reverses the order, gallium, arsenic, gallium. Let me just zoom out. How am I doing on time? Okay, maybe I just finish this. So to make it a little bit more to make it like a better quantification here, you might want to do like a double Gaussian fitting, right? And then I implemented here, and I want to show you for like one example, so you can extend this to a 2D, right? So if you want to do a double Gaussian, so you have to define that first, right? With your different parameters, which can be always be like optimized depending on the sample, depending on the what you want to determine, depending on the spacing between the atomic columns, etc. So there are many things that you can change, but the idea is just to have one column of atom, like this double Gaussian function feeding one column, one atomic column, right? So you have like an X and Y Gaussian here. So one thing that I do here is just like get the coordinates in coordinates, right? The same ones that we determined previously, right? From that, that will be your initial guess for the center of that specific Gaussian, and then we start feeding, right? So this is you got the initial guess from the maximum, and then you start feeding the curve for each one of them, right? So at the bottom here, just to make a little bit more clear. This one takes a little longer because it consumes a little bit more of CPU here because it's a feeding process, right? So and then we are doing here for many atomic columns at the same time. But what I want to do here is just plot one for you to show. And then here it comes. It might take like a minute. And then one thing that you might have noticed here, so any for all these plots, we can bring any of the functions that we did on the first notebook to this one. So you make like more like visually appealing. You can change color maps as well, and you can add, scale bar, etc. So once you have that kind of like framework, you can just like basically like change the image that you trying to analyze. If you're doing that, I think when I ran this morning was about 2 minutes. Let's see. And the last thing I want to cover here quickly is this. Yeah, there we go. So that's one of the atomic columns, and this is like the fitting of that. Just like 1D plot. I had for like 2D plots, but it was not. It didn't look nice. But you're welcome to try that. You just do like a 2D plot of a Gaussian using those two. In this case here, I use X. You can use like X and Y, and just plot that. So you see that it fits like very well, and then determines the position like much more with much more accuracy than the simple function that was like off the shelf, right? You just got from the SK image. So that's what I want to add here. And this one is the Bayesian framework to be even more precise in this case, and actually counts how many columns you have within the image, right? Because you might be a little bit it might add some um, uncertainties if you do just like the peak finder, or if you just do only the double Gaussian. This one's even more even more accurate than those than the double Gaussian. So I added here. So you're welcome to run. I'm not gonna run here because it's gonna take some time, and I just ran for like a couple of columns. That helps to estimate the parameters for the feeding. So that helps like to be even more precise in that case. So few things before I finish, because it's like 11:51 now. All these notebooks will be available, number one. Two, all of them I have a little bit of explanation of the functions that I use, right? So as you probably have noticed. And just, of course, welcome to check them online, right? It's just a way to guide you on this. And like I mentioned, this is only 2D data sets. So I have like for 3D EDS EOS, like in situ, where I did this segmentation of this video here, for example, which is very small. But anyways, that can apply like some segmentation method to like follow how the sample evolves. A couple of examples for the stem, and then this is example for Fib tomography EDS. So this is an evolving repository. So you're welcome to add anything that you want, right? And then use as you wish, right? But always be careful, like, check everything before if you have all the packages. And then of course you can contact me and I can help you set that up. This will be, I have to push the the latest modifications here, but it will be probably available today. But this is the URL for that. So some of the data sets are a little bit large. They are not here, but I provide a link in the notebook so you can download that to your local machine. With that, so this is again uh, the GitHub address. And then, of course, a lot of people help this. So Epic team, always very helpful, like providing a lot of data and then going like beyond, to extract more from the machines that they manage. And this is my email. You can contact me anytime.